So, last class we discussed two field test, that is your pumping test. So, I discussed this pumping test and sludge test, that means it is a instantaneous insert of sludge into observation wells, either it is a falling head test, manual and electronic water level measurement before, during and after sludge insertion, and continued until water level has recovered. And now you come just go back to how this installation of monitoring wells. If you look at here, this is a broad picture of how this wells have been installed, and this is your aquifer, where this is one well is your discharge well, other two wells are observed well. So, at a constant rate the water has been discharged from this discharge well, and at the same time in the observed well how much water level has fall down, that can be measured by means of mechanically or by means of electronically. There are two measures. So, as I said, mechanically you can put a scale inside and you can find it out how much water level in terms of depth has been decreased. This is another typical test of pumping test has been conducted in the field in United States of America. So, this is a well has been made. In this well, this pumping test is going on from this discharge from this well has been conducted with this by means of pumping of water from the well, and these are the electronic monitoring of this observation wells. Now, another one is by means of pumping test, you can by help of tape, this is called measuring tape. With a probe, this tape can be inserted, measuring tape can be with the probe, it can be inserted inside this well, and depth of the water level means falling down, you can measure by means of this measuring tapes. These are all these arrangements for pumping tests. This is one of the tests which has been done in Central America, pumping test measurements. And what are the consequence of pumping tests? Accurately it reflects performance of aquifer under stress of development, and test transmissibility of formation around well, and for substantial distance can determine radius of influence, how far it will influence, it can be determined. Feasible for fast aquifer, limited feasibility for slow aquifer, require set of equipment and labor, may require installation of well dedicated to the test, and it require lot of managements also. So, this are all about this aquifer. Now, come back to original one, where we are discussing about this permeability measurement by means of tracers or sludge. Earlier we discussed, and I have shown that basic things. So, tracer is a dike or salt or maybe a radioactive material. So, this can be put inside the soil, inside this water, so that this flow inside the water by means of tracer you can trace, and you can find it out by means of differential of head between the two wells, you can find it out what is the coefficient of permeability. Now, this is the formula used to find it out coefficient of permeability from aquifer test. This is our discharge well, this is our discharge well as I earlier shown. This is two measured wells where this measurement has been made, means in this well if you look at this, these are the piezometric surface. In first well, once this discharge or this pumping test has been conducted, what is the head of this and what is the head of this H2 minus H1. So, coefficient of permeability K can be find it out Q ln R2 by R1 2 pi H H2 minus H1. K is your coefficient of permeability, and if you look at here, R is your distance of this discharge well, distance of this well from this distance of the observed well R1 is from your discharge well. This is your distance. It may be a radial distance, it is not a straight, it may be go in this direction, in this direction, in this direction. In radially you can place it, and R2 is also radial distance of the observed well. These two are the observed wells. Two are the observed well, and R2 is your radial distance of your second observed well from this discharge well. This is your discharge well. So, then R is nothing but where your piezometric head is there. If you look at here, this R is your radial distance from where this head, where this H at this level piezometric surface water level is there, and H2 minus H1 is nothing but is your head difference compared to two observed wells. H2 is head in second well, second observed well, H1 is your first observed well. From this you can find it out coefficient of permeability. This is a typical example. A pumping test was performed in a well penetrating a confined aquifer to evaluate the coefficient of permeability of the soil in the aquifer. Means this has been given data, from there you can find it out coefficient of permeability. So, it is said equilibrium discharge of water from the well is 200 gallon per minute. Discharge is generally gallon per minute or cc per minute or cc per second, cc per hour. This is your discharge Q. Water level H1 and H2 15 and 19 feet at distance from the well R1 and R2 is 60 and 180 feet respectively. Thickness of aquifer is equal to 20 feet. So, find it out coefficient of permeability of the soil in the aquifer. If you look at here H1 and H2, this is your H1, this is your H1 and H2, it is about 15 and 19 feet, and discharge observed from the discharge well is 200 gallon per minute, and thickness of the aquifer is equal to 20 feet. Thickness of the aquifer means this is your thickness of the aquifer. This thickness of aquifer is your 20 feet, H is equal to 20 feet. Now, putting this formula, first you convert is your discharge gallon per minute to either you can convert into feet cube per second or meter cube per second. Discharge is meter cube per second or feet cube per second. So, it has been converted to feet cube per second. So, it is 0.4456 feet cube per second, and coefficient of permeability it can be found out from this formula Q ln R2 by R1. Q is your, this is your discharge which has been observed from here, and this is your R2 distance of your observed well to observed well 1, and 2 pi H. H is your thickness of your aquifer, this is your 20 feet, and H2 minus H1 is 18 minus 15 feet. So, this will be 0.00130 feet per second. Now, coefficient of permeability is 0.00130 feet per second. One is your confined aquifer, other is your unconfined aquifer. Confined aquifer means the aquifer has been confined between these two layers. So, another one is your unconfined aquifer. In unconfined aquifer you can find it out K is equal to Q ln R2 by R1 pi H2 square minus H1 square. So, same way in this aquifer, unconfined aquifer. So, one part is impervious, other is open. So, in this case H1 and H2 as I defined earlier, R1 and R2 as I defined earlier also. Q is the discharge obtained from your discharge well. Now, empirical relationship for coefficient of permeability, how to find it out empirically? If you know D10, D10 is it is your size of this, means 10% of the particle size finer than that particle. D10 you can get from your sieve analysis. So, coefficient of permeability K is equal to C1 into d10 whole square for uniform sand in loose state. Remember, it is in loose state, and this is for we are discussing right now for sand. So, K is equal to 0.35 d15 whole square for dense or compacted sand. K is equal to coefficient of permeability, you can get it cm per second, and C1 is equal to 100 to 150. This is a this is not constant, this is 1 by cm second. It has been found out from this coefficient experimentally, it has it got. So, effective grain size d10, this is in cm. So, similarly, d15 is your soil particle diameter corresponding to 15% passing on the grain size distribution curve, 15% passing on the grain size distribution curve in mm. Is if it is d10, then it will be 10% passing on the grain size distribution curve, it will be d10. Now, coefficient of permeability for common natural soil formation, if you look at here, this general the range has been given in terms of meter per second. River deposit, these are the data, we have also data from Indian sand also, these are the data I have taken from some of the reference. These are the data for US soil, United States of America. So, it generally river soil is varying 10 to the power minus 4 to 10 to the power minus 4 to 10 to the power minus 3, and glacial deposits it is varying 10 to the power minus 3 to 10 to the power minus 6, and marine and offshore deposits it is varying again 10 to the power minus 5 to 10 to the power minus 6 or minus 6, 7, even if for clay it is less than 10 to the power minus 9. Now, permeability and drainage characteristics of soil part 2. If I classify this coefficient of permeability, try to understand this chart. I am making it from bigger size to means permeability cm per second 10 square to 10 to the power minus 9. I put in a scale 10 square to 10 to the power minus 9. So, coefficient of permeability, how this scale is varying widely. If I start with this soil type clean gravel, gravel means these are the all clean boulders, big sizes. For this clean gravel, generally this is varying about 10 to the power 2 to 1.0. Now, clean sand and gravel mixture, it may be sand plus gravel mixture, that means these are my gravels with the sand particles, it is a mixture of sand and gravel, it is varying between 10 to the power minus 3 to 1. Look at the range, for clean gravel it is varying from here to here, for clean sand it is varying from 1 to 10 to the power minus 3. Very fine sand means particularly this is the range we call as a good drainage, that means 10 to the power 2 to 10 to the power minus 4, whatever the coefficient of permeability, that we say it is a good drainage, that means in that soil water will pass very easily. Good drainage meaning water will flow inside the soil, immediately water will come out from the soil, means its permeability capacity is very high. Now, between 10 to the power minus 4 to 10 to the power minus 6 in soil mechanics we say it is poor, and 10 to the power minus 6 to 10 to the power minus 9 if the coefficient of permeability we say impervious. Impervious means absolutely if water is there inside the soil, very difficult water to come out or drainage will be happen. Where drainage is not going to happen, that case it is called impervious. Now, very fine sand, organic, inorganic silts, mixture of sand silt, look at the soils. First part is your very fine sand, organic and inorganic silts, mixture of sand silt, clay, glacial till, such stratified clay deposits. This range is lying between 10 to the power minus 3 to 10 to the power minus 7, and impervious soils, particularly clay below the zone of weathering. If I can say clay soils below the zone of the weathering, this I can say that this is particularly impervious, that means permeability is not practically possible. Remember, impervious, it is not necessary that permeability is not possible, permeability is there, but look at this 10 square and 10 to the power minus 9, how far the permeability is varying. So, that is why it is called impervious. So, now how to find it out? Direct determination of coefficient of permeability K. So, direct testing of soil in its original positions, particularly from between 10 square to 10 to the power minus 4, look at this range. Either you can find it out from the field pumping test, if it has been properly conducted. This is a best test for in situ pumping test, where you can find it out K directly in the field. Then in case of laboratory, you can find it out by means of constant head permeability. Constant head permeability means the head is constant, as I explained earlier. By means of constant head permeability you can find it out K. Now for other part of the soil, how do we find it out? This is for clean gravel, clean sand, you can find it out in the field by means of pumping test or by means of constant head permeability test. Now indirectly, how do you find it out in the laboratory? For soils varying with your coefficient of permeability 1.0 to 10 to the power minus 9, falling head permeameter, though this is unreliable in the laboratory, you can find it out by means of falling head permeameter test. These three, particularly very fine sand, organic soil, glacial till and stratified clay deposits, these three soils you can indirectly find it out K by means of falling head permeameter in the laboratory. Then computation of grain size also you do for fine grain soils, find it out grain size, and indirectly by empirical correlation also you can find it out. Then go to the next part, permeability in stratified soil. In general, in the field it is not possible that soil is only one component. If it is a sand, it is not possible that throughout all will be sand. So, this is a different soil, this is a different soil, this is a different soil. This is called stratification. So, K1 is different, K2 is different, K3 is different. So, stratification may be in y direction different, may be in x direction difference, may be x as well as y direction it is different. So, for this Ky you can get it, this is your how it has been derived. Ky permeability in y direction for stratified soil deposit you can get it H by H1 by K1, H2 by K2, Hn by Kn. With this help you can find it out permeability in y direction for stratified soil. Similarly, in x direction also you can find it out, because as I said stratification may be in x direction as well as y direction. That means you can find it out K1 H1, K2 H2 plus Kn Hn by H. If you look at this, both this formula, one is your total height for y direction divided by H1 K1, H2 K2, H3 K3. So, other is your in x direction K1 H1 plus K2 H2 Kn Hn divided by your total height. Now, one of the example, another example, a non homogeneous soil consisting of layers of soil with different permeability. Average coefficient of permeability in horizontal and vertical direction, it has been asked to find it out. So, each layer by means of laboratory test Kx and Ky you got it, it is 10 to the power minus 3 and 10 to the power minus 4 cm per second. For layer 1 its height is 1.5 meter. Similarly, for layer 2 its height is 2.0 meter, layer 3 it is 2.5 meter. With help of layer 1, layer 2, layer 3 you can find it out by means of using this formula, you can find it out Kx and Ky. Average permeability in horizontal direction, it is 4.16 into 10 to the power minus 4 cm per second. Average permeability in vertical direction, it is 9.96 into 10 to the power minus 6 cm per second. another one is your related to permeability, particularly irrigation projects. What are the different tests of soils required? That means irrigation projects means particularly canals. In the irrigation projects, it required pre-construction, during construction, also post construction. The soil tests required during pre-construction means before construction, during construction when the construction work is going on, then after construction is over, after few years you can do the also post construction. So, tests for spillway constructions, like you can for irrigation projects you can do, because this is a continuous flow of water, particularly in irrigation projects in the soil. In situ permeability test you will have to determine, because it is related to permeability, that is what I am discussing. By means of single Parker method or double Parker method to decide about this grouting, then field rock shear test, also some geological report you need. So, basically geotechnical engineering, as far as geotechnical engineering is concerned, so you have to do this in situ permeability test, particularly irrigation projects like canal. Then test for CD or CM works means collect undisturbed soils and differential free swell test and plate load test. Free swell test means particularly irrigation project, the soil sample is there. The soil sample, what will happen during summer season, it will try to shrink. During winter season, as the water added, it will try to, the soil will try to swell against loading. It is sometimes we say free swell or swell against the surcharge. That means with application of water it will try to swell. This is most important, particularly irrigation projects. So, generally in the lab we do this swell test by taking the soil sample, putting in odiometer test, odiometer equipment, then apply certain loading, then apply water, then we allow the soil to swell, say for a day, 2 days, 3 days, 4 days, months together. So, we record how much swell pressure we get it or swelling we get it over the period of time. That means swelling is going on, somewhere else it remains constant. That means no more further swelling, at that point we will stop the test. So, mechanical analysis, now it is called test on CNS material or CNS soil. What is CNS? CNS is cohesive non-swelling. Remember, CNS is nothing but cohesive non-swelling soil. C for cohesive, N for non, S for swelling. That means we will do test cohesive non-swelling soils, generally it has been used for irrigation projects. So, mechanical analysis, we do sieve analysis and hydrometer analysis, Atterberg limits, liquid limits and plastic limits, it has been discussed, and swell pressure test. Now, requirement to use as CNS soil, what are the different requirement? Means CNS material, if I say CNS cohesive non-swelling soil, if I say how this profile is varying, what kind of material we can say cohesive non-swelling soil. For this, the gradation curve it says gravel should be 0 to 10%. How do you decide gravel? In 2 mm sieve, percentage of soil particle retained is about 0 to 10%, then we can say that gravel is about 0 to 10%. Similarly, sand, this sand is varying from 2 mm to 0.06 mm if it is 30 to 40%. Then silt also 30 to 40%. Clay, clay is your which is less than 0.002 mm, it is generally 15 to 20%, and liquid limit should be between the range of 30 to 50%. Plastic limit in the range of 20 to 25%, and swelling pressure is your less than 0.10 kg per square centimeter. These criteria is best for your CNS soil. cohesive non-swelling soils to be used in irrigation projects. Example, in canal. Generally in village areas, a long canals has been constructed over which water has been allowed through the canal, so that people can utilize water for land purpose. So, over the period of time what will happen, the soils we are getting kind of a cohesive soil. To make it not to be swell more, we will have to add CNS material, cohesive non-swell soil. With this cohesive soil, these are the material to be added, so that complete soil, if I take it into 100% complete soil, gravel will be 0 to 10%, sand 30 to 40%, silt 30 to 40%, clay is your 15 to 20%. So, liquid limit is 30 to 50% and plastic limit is your 20 to 25%. This has been given by Indian Standard, Bureau of Indian Standard, or we generally say BIS, or in terms of it is Indian Standard. It is a codal provision 9451 1994. What should be your range of CNS material in terms of particle size, in terms of liquid limit, in terms of plastic limit, in terms of swelling pressure. If you look at here, these are the three things required for your cohesive non-swell soils. Mechanical analysis, that means hydrometer as well as sieve, Atterberg limits, liquid limit and plastic limit, and your swell pressure test. If you look at here, this is your mechanical analysis, that means this is your sieve analysis and your hydrometer analysis, and this liquid limit and plastic limit is nothing but is your Atterberg's limits. Atterberg limits is your liquid limit, plastic limit and shrinkage limit, as I discussed earlier. And swelling pressure test, you can do it in the laboratory by taking this material, mixing with the soil, so that the pressure should be less than 0.10 kg per square centimeter. Now, what kind of filter you are going to provide? What are the tests for filter? This is also coming in geotechnical exploration and measurement. You should know why this filter has been provided. Generally in a dam also, if I look at the example, simple example, you might have seen this R dam. So, dams has been provided to storage purpose this water. So, what will happen, this dam, there is a steady state seepage flow of this dam initially. If you look at here, instead of allowing water to pass through, if this is my upstream and this is my downstream, US is your U for off, S is your stream, D for down, S for stream. Water, generally we allow water to pass through the dam from upstream to downstream. If we do not provide the filter, what will happen? Water will flow from upstream and it will cut somewhere else in the downstream. Over the period of time, what will happen? This downstream will get fail because of water is passing through. We do not want the dam should be failed because of this high passage of water through inside the body of the dam. To prevent this, generally filters has been provided at the base of the dam. It may be a sand filter or it may be geosynthetic filter. It may be sometimes we earlier days they called as a sand blanket also. What will happen? This seepage line has been changed and it will pass through your filter. So, this filter will collect water from upstream and pass through here, and by means of filter, because filter is a property, it will allow water to discharge, immediately pass inside. So, water will collect from upstream and allow to flow inside this dam and collected in the filter and safely discharge here. So, that means we are not allowing water to flow inside this dam. It is allowing water to flow and collected by means of filters. So, these filters are required for geotechnical testing purpose also. It is related to your coefficient of permeability. These are the material related for your coefficient of permeability, because the moment you say filter, that means you want what is its permeability, how much discharge it allow per second or per minute or per hour, what is the quantity of water should pass inside this filter. That means gallon or cc centimeter cube per hour or per minute or per second, that you will decide. So, what are the tests for your filters? Mechanical analysis, generally sieve analysis, hydrometer analysis and gradation curves. As usual, it is complete sieve analysis and hydrometer, and you will have to find it out how your gradation curve. If as I explained earlier, if this is my percentage finer versus this is the diameter of soil, how the gradation curve is varying. This is called nothing but is your gradation curve. How the gradation curve is varying means this gradation curve is required for your filter design for this filter. So, for filter these are the test mechanical analysis we need, sieve analysis, hydrometer analysis as well as gradation curve. Now, what is as per IS standard? Bureau of Indian Standard 9429, this is the number and this is the year 1980. Need for filters. Look at this paragraph. Transition filters are required between impervious zone of fine grained soil and pervious zones or drains of coarse material to prevent migration of soil grain from former to laster. As the direction of the seepage is towards the upstream phase at the time of drawdown, such filters are needed both on upstream and downstream side. Look at the meaning, it preserve, the moment filter has been applied, it only allow water to pass, remember it only allow water to pass, it does not allow soil along with water should pass. The moment the soil flow means water flow starts inside this body of the dam, what will happen? Soil plus water, it will flow inside. So, here soil will be filtered and water will pass inside. So, next class we will discuss about this complete design of this filter material, what are the test requirement.